We have already learned about the principle of superposition and the wave equation. In this session we would study systems capable of producing sound waves, which are also known as acoustic waves. This topic is not altogether new, and I know that you have studied some aspects of this already at the high school level. There are three main points that I wish to emphasize at the outset. The bulk modulus is an important parameter for fluid systems. It is the ratio of volume stress dP to the fractional change in volume dV by V, also called the volume strain. The negative sign ensures that the sign of the parameter would be positive when pressure increases over the system, leading to a negative volume strain. For the sound pressure field, one can show that the isothermal Bull modulus is just the threshold pressure, whereas the adiabatic modulus is larger by a factor gamma. Making use of the polytropic EEOS of the fluid medium in which the pressure is seen as varying with the density, we see why the volume strain is just the fractional change in density, while the STRE is the differential of the right-hand side of the EEOS. Then make use of the specific instances of the EEOS for isothermal and adiabatic cases. We evaluate the bulk modulus. The adiabatic bulk parameter is higher as it takes more stress to compress a volume from which heat is not allowed to escape. If heat is not allowed to escape, temperature increases and the constituent particles have more kinetic energy. Consequently, they offer more resistance to being bottled up in a smaller volume. This problem shows how to estimate the bulk modulus of the Earth's crust, given the measured values of the sound speed and the density of the crustal material. The sound speed, bulk modulus connection, covered in the last lecture, is employed to get the sound speed. Our discussion becomes slightly more technical with the introduction of some standard sound field parameters. No new physics, just some new names for quantities we already know about or related to them. These are the dilatation, which is none other than the volume strain, and a reciprocal quantity, condensation. For small changes, one of them is just the negative of the other. The dilatation is also equal to the spatial derivative of the wave field. The excess pressure is found to be related to the bulk modulus, introduced before, and these quantities. To understand the first line of derivation, please refer to the picture of the cylindrical volume in the slide EEOM for longitudinal displacements. Remember that psi x stands for the longitudinal displacement of a particle in the wave field, and that the cylinder extends from x to dx in the unperturbed state, that is, when the wave is not disturbing it. Capital S is the area of each circular cap of the cylinder. When the sound wave is turned in, the left layer of the cylinder is displaced by psi at x, but the right edge is displaced by psi at x plus dx. Thus comes the first line, and the rest follows from it quite simply. Note that a colored line would cancel with a colored line of the same color, and the cancellations are effected after any brackets are removed and factors multiplied together. Equation 2 follows if remember that the mass of the cylindrical parcel do not change on the passage of the wave, it just gets elongated or shortened, and the density within it changes a little. Finally, equation 3 follows if you identify the excess pressure with the instantaneous volume stress. A medium in which the excess pressure is proportional to the volume strain is called a Hooke's law media. This is a problem designed to make you appreciate the smallness of the quantities involved in sound propagation. The quantities are all of the order of a few parts in 100,000ths of the unperturbed quantities. Whenever the pressure differ between the two faces of a volume element in a fluid, a net force acts on the volume element in the direction opposite to that of the pressure gradient. The force per unit volume of the parcel equals the gradient of the pressure field in the medium. This can be easily seen by considering the situation shown in the slide. The net force acts along the negative x direction and its magnitude is calculated by considering the difference between the two faces. We now consider a situation in which pressure differences can be there along all three coordinate directions. Think of the volume element to be cubical, the shape do not really matter. It is clear that the expression for net force will gather two more terms in the pressure derivatives. This leads to the final result. You have seen instances of the volume force before. Just think about how you would have derived the relation d rho dh equals minus rho g if you had known about the volume force by then. If we appreciate that there is such a thing called the volume force, derivation of the sound field equation becomes much easier. We start with the left-hand side of Newton's law of motion as the mass of the volume element times the particle acceleration in the usual way. The right-hand side is given by the volume force times the volume of the element, which cancels out from both sides. Next we equal that the excess pressure is proportional to the dilatation, and the dilatation is none other than the space derivative of the sound pressure field. Thus, with the right constituents, the derivation becomes a one-liner, almost writing out a self-evident truth. In discussing the derivation of the sound wave equation, we have introduced a lot of symbols and interrelationships. We halt for some time to reflect back on these. There is also a new equation at the end, one which relates the excess pressure T, the sound speed, and the condensation. Although the wave equation is originally shown to be true for the particle displacements, all other related quantities, like the excess pressure, particle velocity, excess density, condensation, etc., vary in the same way, follow the same wave equation. We show it here for dilatation, but other relations can be worked out more or less in an identical manner. In the next slide we would specialize to plane wave disturbances and find the amplitudes of the various excitations. With this, we begin to discuss solutions to the sound wave equation. The wave equation permits any solutions in which psi is of the form EFF of omega t plus or minus kx. A sinusoidal disturbance will produce sinusoidal waves. These waves form the heart of acoustics as they are generated from tuning forks, speech, and music. Furthermore, complex acoustic patterns can be mostly described by a superposition of basic sinusoids. We would therefore study how a sine wave excites a fluid as it transports energy from one point to another. To start, we assume a complex exponential progressive wave traveling in the x direction. Omega is the frequency of the driver, like a tuning fork, and k is the wave vector. Since we have chosen b and not k to represent the bulk modulus, there should not be any point of confusion here. Assuming this form, we work out the expressions for the particle velocity u, volume strain psi dash, condensation s, excess density, and, finally, excess pressure. You might want to refer back to screen 8 now. Note that the excess density expression can be best thought about by writing it as rho e by rho naught equal to minus del psi by del x in screen 8, and the equation relating excess pressure to the sound speed appears as the last expression in that slide. If we now examine the expressions for the various quantities, we find that they are all harmonically varying quantities, varying in both space and time. Also, since the modulus of the exponentials are all unity, you can easily read off the amplitudes by reading the coefficients. For example, the amplitude for excess pressure is chi cs square rho naught. As for the signs, well, they correspond to phase differences between these quantities, in much the same way as phase differences arise between the current and the voltage across an inductive element in an AC circuit. We find that apart from dilatation, all other quantities keyed psi by pi by 2 or 90 degrees and are mutually in phase. The dilation is 1/8 degrees apart from the condensation, a fact which makes immediate sense. In the next lecture we would talk about energy transport.